What is going on, everybody? Welcome back to another video of Cupcode 01. Today we're knocking out array sequences, and then tomorrow we're going to knock out one of our first interview questions regarding arrays, primarily dynamic arrays. So in Python with array sequences, there are three different types of arrays. You can have a list array, a tuple, and a string. Now these are all different three types of arrays. You can see that the list is going to be identified by the brackets, a tuple, parentheses with a comma in between them, and then a string is identified in between parentheses with the quotations. What makes all three of these unique in terms of an array sequence is all three of these can be manipulated by indexing. They all support different indexing parameters. So to quickly understand some of the basic theory before we get into even the interview question, to understand how arrays work, we need to understand low-level computer architecture. So what I have here is a memory. Assume this is like your RAM, your random accessible memory within the computer, and each one of these numbers, 2144, 2145, 46, etc., are like address locations. Now memory is stored in bits, but 8 bits is a byte, so we go by bytes when we're looking at this data. And then there's a memory address for each byte. So in this one byte here, 2144, it actually has 8 bits within it. That's how we're visualizing this. Now, what's interesting about, at least with the arrays, is that they're stored and retrieved in big O1. It's a constant time, so it does not matter if you're at the beginning of an array, middle of an array, at the end of the array. If you're indexing its position anywhere along this memory sequence, the big O, the time, is going to be constant regardless of where you're doing it. And again, this is theoretical, but it's also pretty much in practice. So the idea is no matter how much you have stored in memory, if you're using indexing, you can recall it in the same amount of time, regardless of if you're using a list, a tuple, or a string. And also regardless of its indexing position. So if you have a book that's all in one string, if you're indexing the very beginning of it or the very end of it, it's going to be able to have the same kind of a recall time because of its memory address location. Python is represented in Unicode characters with 16 bits, and again, if there's 8 bits in a byte, then 16 bits can be 2 bytes. So in 2146, 2147, if we had the string sample, it would show me an index of 0 in that string is going to have the element S for sample, and it's going to take up 2 bytes within this memory sequence, address 2146, 2147. So if I index 0 or if I index 3, the Python is going to know exactly where in the memory, what address to go to actually recall that element that resides within that list, tuple, or string. So we have sample is 6 characters, it's going to be 12 bytes, because again, it's 16 bytes for 2 bits. 16 bits for 2 bytes, sorry. We have an array here of 6 characters, 1, 2, 3, 4, 5, 6, indexing 0 to 5. Each character is going to take up a cell. So this cell S is actually being composed of 2 different bytes. And then the index describes the location. Of course, 0, 1, 2, 3, 4, 5 is describing our location of our string, tuple, or list. And this is just for knowledge. We're going to be using, the work that we do is going to be higher level abstraction. This is considered low level abstraction, the very lowest level you can get into in terms of arrays. So quickly talking about lists and references. So looking at this image here, assuming we create a list and we named it primes, and it's storing the prime numbers 2, 3, 5. We created this list and it's storing it within these index locations here within memory. So now you know that index of 0, 1, 2, 3 is actually going to correspond to a physical address within the memory in the computer. These are the reference points that it's going to have. Now assume we create a new list. Say we had like a temp list, and we wanted to reference a portion of the list, like if you were splicing a list. The point is, it's not going to create a brand new list. All it does is it takes the temporary list that you created here and it just changes the index assignment of that list to reflect where those elements are within memory. So down here we have, if you want to change an index assignment to a new temp list, say we did temp index of 2, 0, 1, 2, so that's this location here of 13. Right now it's pointing to 13 within the previous list of primes. All it's doing is referencing primes index of 5, which is at 13. It's just indexing. Now temp2 is indexing at 13. It's just referencing that particular element within stored memory. If we want to change it to 15, the original list is not going to change. All that's going to happen is right here, this 2 right now is referencing 13. This 2 will then point over here and reference number 15. It's not going to actually change. It's not going to append or amend this list that exists within primes. It's just going to change its pointer. And that takes us to a topic called pointers in regards to memory, and very crucial at the low-level aspect of understanding computer science and how things are stored in memory and recalled and referenced. But the important thing here is that the original list is not changed. 2, 3, 5, 7, 11, 13, 17, 19. That's not changed. If I change this temp index 2 to 15, it just comes over here and references a different location in memory that's storing the 15. It does not mess with the original list. So we have here the takeaway is new list, create a shallow copy, meaning you're only changing or creating your pointers. You're not duplicating objects in memory. And much of what we're doing is manipulating references and calls, not the object itself. We're manipulating the reference and the calling of the elements. We're not actually changing the physical object that resides within memory. Quick little exercise here. We're importing sys. It's a module within Python. Creating n equals 10 data is an object that we're creating with just an empty list. And then for I in range n, again, n is right now 10, so it's going to be for 1, for 2, for 3, for 5, and it's going to go through this. A is a variable that we're just saying, give me the length of the data. At that point, data, again, right now is an empty list, so at the first point, it's going to say 0. B equals sys.getSizeOf. GetSizeOf is a method that resides in the sys module. And we're saying, give me the size of data. And then I'm printing on the bottom here, we have a string, it says length. Now this, it looks like a dictionary, right? It looks almost like a key value pair that we have here. But what this is string formatting. And what I'm going to be doing is, if you see this, and then look at this. So what this is saying here is at index 0 of format, so dot format index of 0 is going to be A. And A is going to reference this data. So it's saying, I want you to put length, colon, and then I want you to give me the value of A. And I want you to only take 3 integer places. That's all that's messing with right there. And then size in bytes, index of 1, which is going to be the value of B. B is generated here. And we're saying, give me B and take that 4 integer places. Now you'll notice you can also do left and right alignment. So if we're calling for 3 integer places and we only have 1 number, you're going to have 2 and 1 left of it, because it's going to automatically default to right alignment. But that's what this dot format method is. I'm saying dot format A into this position, 0, and format B into this position here when I print my string out. So data.append n, again, this is just saying with my empty list here, append it with the number n. So right now it's empty, we're going to fill it up. So I will run this cell, even though I already have a run down below. And I just want to quickly go through what this means. So a length of 0, because the original data is going to be 0, the length of data starts off as 0. Python automatically reserves 64 bytes in memory, even though the length of the list has not changed yet. And I'm going to bring this down so we can see this image down here. When it goes to length of 1, the size in bytes does go up to 96, but then with the length of 2, the size is still 96. 3, we're still 96. 4, we're still 96. Once we get to 5 elements within our list, now we go up to 128. Python is increasing, and then it runs at 128, 1, 2, 3, 4 instances before it runs up to 92. What is this doing? The point of this is that Python, we don't have to dictate the size of the array before we create it in Python. It's going to grab a little bit more memory than what it's going to need, and it's going to fill up that memory. And when it gets to the point of where it can't fill up anymore, it's going to create a new sized array. It's going to copy over the previous array, and then it's going to almost double what it's doing. Depends on your byte size. So down here, if you have this array that has 4 elements, 1, 2, 3, and 4. So if our length of 0, 1, 2, 3, we're good. But then once we start to get to 4, 5, 6, it's going to have to jump down to a new size array. So that's what we're showing here with B. So B is an empty array, and it's going to take the elements of A, because B is bigger than A. It's going to take all the elements of A, and it's going to point them to B. So here's our elements. Here's our elements. First, A is referencing. Now B is also referencing. And then A is going to become garbage. B, what was B, is going to hold those elements, and it has more spaces here now to take on more elements, more appending of that particular array. And you can see it just changed the assignment to A because this became a garbage array, which we'll get into another time. But the point is, you could even make this whatever the heck you want, and you can just see that it's gonna create a new size, and it's gonna hold it as long as it can, and then it's going to move that array into a larger array of memory so that it can hold those points, but it's not point for point. It will hold it for a certain number of time. And as the length increases, then it will jump to the appropriate size of memory. Of course, until you get a memory error. All right, guys, that's it for today on the array sequencing. Again, we have list, tuples, and strings. They all support indexing. That's one of the main takeaways there. Then we just did some low-level pieces of memory recall and data storing for arrays, and just showing you how exactly those things are stored and how we can jump through how Python can increase its memory size of arrays if necessary. Next video, we're going to be knocking out dynamic arrays, and specifically an exercise, an interview question exercise with 2 different solutions on dynamic arrays. Have an excellent day, guys.